Welcome everyone! In today's lesson, we are going to explore a powerful tool for simulating how systems change over time, known as the Verlet algorithm. Specifically, we will learn how to use this algorithm to model the motion of a dynamical system by working directly with its equation of motion, which is often in the form of differential equations. This is a significant step forward from our previous simulations, which relied on parametric equations that were already solved algebraically. The Verlet algorithm offers a more robust and general approach, allowing us to simulate motion based purely on the governing equation of motion in its original, fundamental form. We will see how this applies to systems obeying Newton's second law. For a one-dimensional system, where a mass m is subject to a force F, its motion is described by an equation of motion. This equation tells us that the acceleration, which is the second derivative of position r with respect to time t, is equal to the force acting on the mass, F of r, divided by the mass m. This is a second-order differential equation. A classic example is simple harmonic motion, where the second derivative of position x with respect to time t equals negative k divided by m, all times x. The left side describes how the trajectory evolves, while the right side represents the force per unit mass. Our main goal in studying such systems is to determine the position and velocity over time, given the force and some initial position and velocity. The Verlet integration algorithm is a numerical method specifically designed to solve Newton's equations of motion. It is very popular in fields like molecular dynamics, simulations, and computer graphics for calculating particle trajectories. There are a few variations, such as the ordinary Verlet and leapfrog Verlet, but in this lecture, we will focus on the velocity Verlet algorithm. The core idea is that if we know the force as a function of position, and thus the acceleration, we can predict a particle's position at a future time, t plus delta t, based on its current state at time t. For a detailed derivation, you can refer to online resources. Assuming we know the initial conditions, position x at time 0, and velocity v at time 0, the velocity Verlet algorithm proceeds in 3 steps. First, we update the position using the formula x at t plus delta t equals x at t plus v at t times delta t plus 1/2 times a at t times delta t squared. Second, we compute the new acceleration, a at t plus delta t, using the equation of motion with the newly calculated position. Third, we update the velocity using the formula v at t plus delta t equals v at t plus 1/2 times the sum of a at t and a at t plus delta t, all multiplied by delta t. It is also important to understand the accuracy of this method. The global, or cumulative, error in position over time when using the velocity Verlet algorithm is on the order of delta squared. Similarly, because the velocity is updated using both current and future accelerations, its global error is also on the order of delta squared. Let us now apply the velocity Verlet algorithm to a concrete example. One-dimensional simple harmonic motion, like a mass attached to a spring oscillating on a frictionless horizontal surface. For this simple harmonic oscillator, the force is given by F equals negative k times x, where k is the spring constant and x is the displacement. This leads to an equation of motion where the acceleration, a, which is the second derivative of x with respect to time t, equals negative k divided by m times x. Here, x of t the position, and v sub x of t, the velocity which is also the time derivative of x, are the dynamical variables that describe the motion of the point mass m. The constants k and m characterize our specific oscillator. We will use the velocity Verlet algorithm to update these variables x and v's at each time step. For our numerical setup, we will initialize the system with a starting position x at time 0 equal to x naught, which is 0.1, and an initial velocity v at time 0 equal to v naught, which is 0. We will set the spring constant k to 1 and the mass m to 1. The time step, delta t, will be the period t divided by a large integer n. From Newton's law, the acceleration at time t is a of t equals negative k divided by m times x of t. To update the position, we use x at t plus delta t equals x at t plus v of t times delta t plus 1/2 times a of t times delta t squared. After finding the new position, we then update the acceleration using a at t plus delta t equals negative x at t plus delta t, assuming k and m are 1 for simplicity here. The following Python code block will simulate the simple harmonic oscillator using the velocity Verlet algorithm we just discussed. And it will use func animation from matplotlib to create a visual representation of the motion. First, we import necessary libraries like NumPy for numerical operations and matplotlib for plotting and animation. We then initialize our physical parameters: initial position x0, initial velocity x.0, spring constant k, mass m, angular frequency omega calculated as the square root of k divided by m, and the period t. We use dictionaries to store the time series for position x, velocity x dot, and acceleration x. The simulation will run for a total duration of t last, which is set to a few periods of oscillation, and we define a time step delta t based on dividing the period into nt segments. Inside a loop that runs for each time step, we first calculate the acceleration at the current step using a equals negative k over m times x. Then, we update the position to the next time step using the Verlet formula. Current position plus velocity times delta et plus 1/2 acceleration times delta et squared. Next, we calculate the new acceleration based on this new position. Finally, we update the velocity using the average of the old and new accelerations. After the simulation loop, the code sets up a plot. It marks the origin and the initial position of the oscillator, and draws a horizontal line representing the path of motion. An update function is defined for the animation. This function takes the frame number n, retrieves the corresponding simulated position x at n and y at n, which is 0 for 1D motion, and updates the position of a plotted circle representing the oscillator. The animation is then created using func animation and displayed as an HTML5 video, allowing us to observe the simulated oscillation. Now let us extend our use of the velocity Verlet algorithm to simulate two-dimensional projectile motion. In this case, the acceleration in the e direction, which is the second derivative of y with respect to time t, is constant and equal to negative y, the acceleration due to gravity. The acceleration in the x direction, the second derivative of x with respect to time t, is 0, assuming no air resistance. For the y component, the Verlet algorithm involves updating the position y at t plus delta t using y at t plus v sub y at t times delta t plus 1/2 times a sub y at t times delta t squared. The acceleration a sub y at t plus delta t remains negative g. The velocity v sub y at t plus delta t is then current v sub y plus 1/2 times the sum of current and new y accelerations, all times delta t. Initial conditions are y at 0 and an initial y velocity v sub y0, which is v0 times sine theta. For the x component, the position x at t plus delta t is updated similarly using x at t plus v sub x at t times delta t plus 1/2 times a sub x at t times delta t squared. The x acceleration, a sub x at t plus delta t, is 0. the x velocity v sub x at t plus delta t is then current v sub x plus 1/2 times the sum of current and new x accelerations, all times delta t, which simplifies because x acceleration is 0. Initial conditions are x at 0 and v sub x 0, which is v0 times cosine theta. The Python code block performs this simulation. It starts by importing necessary libraries and setting up physical parameters like the launch angle theta, initial position, gravitational acceleration g, and initial speed v0. It then calculates initial x and y velocities and determines the simulation duration and time step. Kinematic quantities like position, velocity, and acceleration for both x and y components are stored in dictionaries. The code also defines functions for the analytical solution of the trajectory, which will be plotted for comparison. The main simulation loop iterates through time steps, applying the velocity Verlet updates separately for the x and y components as we just described. Finally, it prepares and displays an animation of the projectile's motion, plotting both the simulated path and the theoretical trajectory. Next, we will explore how the velocity Verlet algorithm can be applied to simulate uniform circular motion. In uniform circular motion, a particle moves along a circular path at a constant speed. The position vector r of t continuously changes direction. The velocity vector v of t is always tangent to this circular path, and the acceleration vector a of t, known as centripetal acceleration, always points inward toward the center of the circle. The acceleration is given by the vector equation a of t equals negative omega squared times r of t, where omega is the angular velocity and r of t is the position vector. To initiate purely circular motion, if we start at an initial position r0, for example, at r, 0 on the x-axis, the initial velocity v0 must be perpendicular to this initial position vector, and its magnitude must be omega times r. So, v0 would be 0, omega r. The velocity Verlet algorithm updates position and velocity in vector form. The position vector at t plus delta t equals the position vector at t plus the velocity vector at t times delta t plus 1/2 times the acceleration vector at t times delta squared. After calculating the new position, we compute the new acceleration vector using a at t plus delta t equals negative omega squared times r at t plus delta t. Then, we update the velocity vector using v at t plus delta t equals v at t plus 1/2 times the sum of the acceleration vector at t and the acceleration vector at t plus delta t, all multiplied by delta t. This method is well suited for such conservative systems because it generally conserves energy well. The provided Python code implements this. It imports necessary libraries, sets parameters like angular velocity omega, total simulation time, and the number of time steps. It initializes arrays for position, velocity, and acceleration. The initial conditions are set for the particle to start on the x-axis with an initial velocity purely in the EI direction, and initial acceleration is calculated. The core of the code is a loop that iterates through time steps, applying the velocity Verlet equations to update the two-dimensional position, then the new acceleration, and finally, the new velocity. The simulation results are then animated using matplotlib, showing the particle moving in a circle and tracing its path. In this lesson, we have thoroughly explored the velocity Verlet algorithm, a robust numerical method for simulating the motion of dynamical systems. We learned that it operates directly from the system's equation of motion, typically a second-order differential equation derived from Newton's second law. We saw its step-by-step application, first updating position using current velocity and acceleration, then recalculating acceleration based on the new position, and finally updating velocity using an average of old and new accelerations. This approach, as we observed, maintains good stability and energy conservation, particularly for long simulations. With errors typically on the order of delta squared, we applied this algorithm to three distinct physical systems: one-dimensional simple harmonic motion, two-dimensional projectile motion under gravity, and uniform circular motion, illustrating its versatility. Each example involved setting up initial conditions, defining the force law or acceleration, and iteratively stepping through time to trace the trajectory. The animations helped visualize these motions. And an important takeaway is to consider how these simulations, based on fundamental equations of motion, compare in their nature and output to simulations based on pre-solved kinematic equations. Understanding this distinction highlights the power and generality of numerical integration techniques, like the Verlet algorithm in physics and engineering.